Okay, there we go. We are in week 9 of our series Get Started in OpenSees with STKO. Today we talk about the analysis command. We started a bit earlier because it's a difficult topic. It will require a lot of talking, and our slides, there's a lot of stuff written on it. It's less graphic and more content this time. We don't have exercises, practical exercises. It's just us discussing the setup of the analysis command and what's in it and how we can use it to our advantage in our modeling. We're going to talk about it today and next week with these double features. And of course, next week too, we will have, we will have another one at 5:30 p.m. So what I'm going to talk about today, mostly, it's only a few elements of the analysis command. There's a lot of setup that you have to take care of when you create an analysis command. But today we're going to talk about all the things that, let's say, are the same for any kind of analysis that you want to run. So it's not like you have to set up the analysis in the same way, but there are these 5 elements of the analysis command that have the same options for any type of analysis. Instead, next week, we're going to talk about specific things related to static or transient analysis. So just remember these things, you can apply this concept, you can apply them on either static, transient, eigenvalue, any analysis that you want to run. My presentation has a huge lag. Yeah, and I have a little disclaimer for you guys. It's a very nerdy presentation, so there's a lot of math, and I'm not going to explain all the theory behind things, but it's important that you keep an open mind and interest mind, let's say. So we said in the OpenSees abstraction, the analysis command contains all of these things. I already said we're going to talk about these 5 elements, but not the integrator, because the integrator, which is the thing that decides how you iterate from a last step from the last step to the current step, that's something that changes if you're running static or transient dynamic analysis. So we're not going to talk about this today. As you remember from last week, the analysis command is the last required step to set up a basic analysis in STKO. And you do it through the analysis steps, you put it at the end of your list. And these are the default options that comes out. So just for you to know, if you want to run a simple static gravity analysis in a model that doesn't have any specific interactions or is not particularly large, and does not have any, let's say, complex concept to address, this setup, it's okay. You can just click and click OK, and it's gonna be fine. But it's nice to learn what all the things in the drop-down menu means and what you can do with them. So this is the parts that we're gonna address. Let's say the red things are the most complex things, at least in my opinion. Orange ones are the ones that we can tackle a bit more clearly and understand better. The numbers is really, really easy concept to understand. So let's say I'm going to tell you a little about the number, a lot about the constraint handler and the convergence test. And I would have liked to tell you a lot about the solver and the algorithm, but maybe we need a university course for that. So we're going to just say what you need to know in order to use the software and be successful in your analysis. So let's talk about constraint handler. The constraint handler is an object in OpenSees that determines how the constraints are enforced in the analysis. It's how OpenSees will apply the boundaries in the system matrix. So you have a global stiffness matrix of your system, and on that matrix, that matrix will have to be modified in order to apply the system boundaries. So the matrix will define all the DOFs of your structures related to all the nodes of your structure, and on those nodes you apply some conditions on the kinematics of the structure. And to enforce those conditions, there are specific mathematical tools in order to do that. So sometimes it's a specific value of a degree of freedom. Like if you want to fix a node, you apply a 0 value to that degrees of freedom. Or if you want to apply a prescribed displacement, you apply a specific value different from 0 to a DOF. Or of course, what we talked about in week 4, in week 5, I think, in the interactions, there is a specific relationship between degrees of freedom. So if you want a node to move exactly like another one and vice versa. Of course, we have to make the distinction. We already made it before. It's really hard to stop saying master and slave. So I'd like to make an effort also today for myself too, to distinguish between retained node and constrained node. So retained node are the ones to which the DOFs is applied. The DOFs condition is applied, and the constrained node are the ones that have to move or behave exactly like the retained one. At times, the distinction is very relevant, so which one is which is very relevant, and in other instances, they're interchangeable. Just remember that you can have a lot of problems if you choose your constraint handler wrongly. So this is actually a very important topic, even if it's just one setting of your analysis command. There's 4 types of handlers: the plain constraints, the Lagrange multiplier, transformation, and the penalty method. They differ in between each other for a lot of things. The way they transform the system matrix, if they can handle non-homogeneous constraints, so constraints that are different from 0, multiplying constraints, if they need you to be careful about which one is the retained and which one is the constrained node in a pair, and if you can use them with any conversion test or not. We will talk about what is a conversion test afterwards, but I'm sure you guys already know more or less like what is a conversion test. It's something that makes a checks and determines if the solution that you are obtaining is feasible or not, if you can go on with your analysis or not, based on a specific tolerance that the user set up, that you set up. So plain constraints, first type of constraint handler. This is our matrix. What does the plain constraint does? He condensates the matrix, so erase some of the DOFs from the global stiffness matrix and reduces its size. This is really, let's say, useful because this means that your model is lighter, so there's something less to be computed in your matrix. So in this case, you can distinguish between retained degrees of freedom and condensed degrees of freedom. Of course, with this, let's say, with this advantage, it comes a lot of limitations. It's important to pay attention which is which. So which is the, sorry guys, some more people. Which is the retained node and which is the constrained node. For example, just think about it. If you have a constrained node that you are tying to more than one retained node. So because, I don't know, because you made a mistake or because you wanted to apply a double constraint to that node. Once that node is erased from the matrix, then when it's time to recall it back, it will not be found. So it will be a problem if you want to enforce a specific over constraint on a node when you use this kind of constraint handler. The same matrix condensation is also using the transformation method. So just remember this definition because it's the same one for the transformation method, is to erase some of the DOFs from the matrix and reduce its size. How is it limited? So you cannot really use this kind of handler if you have non-homogeneous single point constraints. So if you have a prescribed value to a node, to a DOFs of your structure, you cannot use this kind of handler. And you can only use it if constraints are an identity matrix. So only if you're using single point constraints. No multi-point constraints can be used with the plain constraints. As I said before, with great advantage comes a lot of limitations. So the only multi-point constraints you can use the plain handler with is the equal DOF, because of course in the equal DOF, there's no difference between the master and slave. It's like you're saying this has to move exactly like this. So this you can do, but the other things, like in this case, the condensed node have to be equal to 0, and you will not be able to use this kind of interaction with this handler. Then we have the Lagrange multiplier. What happens in the Lagrange multiplier? Instead of reducing the size of the matrix, we're increasing it. The constraints are handled by enlarging the size of the matrix, and there's no condensation. Instead, one equation is added for each constraint that need to be enforced. So the transformation of the matrix implies that if you knew already before what was the shape of your matrix or its characteristic, for example, if it was symmetric positive definite, I don't know how well you guys know about this stuff, but for example, a positive definite matrix is a matrix with only strictly positive finite eigenvalues. So that's not true for all the models. Sometimes you know that it is. For example, if you have a linear model or only strain hardening behavior, But already in a model that's a bit more complicated, like with softening or non-associated plasticity, the matrix will not be positive definite. So let's just say you have to be careful if you apply the Lagrange multiplier with the fact that the matrix changes shape and characteristics, because then the system solver that you use will have to be applied to that matrix. So if you use a solver that refers to only symmetric positive definite matrices, and then you cannot really use this kind of handler on it. Hi, Halia. Yes, of course, recording is being, like the course is being recorded, so you will have it tomorrow on YouTube. Don't worry. I know maybe someone arrived a little late. You want to know what we talked about before, or you guys have to do something right now. Anyway, let's go further. So Lagrange multiplier different from plain constraints because we're not condensing the matrix, but we're actually increasing its size. What are the limitations here too? I mean, it's not really a negative fact that we have a larger matrix overall, but what can happen is that also here you need to be careful about the pairs of restraint and constraint, because, for example, in the same case, if you have a constraint node reference to two retaining nodes, so you will need two extra equations that will be linear independent, and then we create a singularity in your matrix. And also, if you have over constraints, this should not really work because there's also a double extra lines, a double extra equations in your problem. And this does not create a singularity in OpenSees because OpenSees takes care of over constraints with this kind of handler. But at the same time, you will not have that second constraint that you set up. So just remember, with these multi-point and double constraints and over constraints, there's a lot of problems with these two handlers. And of course, it's not so intuitive, but another thing you have to take care is that when you choose a convergent test, you cannot use a displacement increment test with the Lagrange multiplier. And this is because the new rows that are added to the matrix, which are solution vectors, so in terms of displacement and rotation, they also contain forces. And so that kind of changes the order of magnitude of the vector. And if you try to apply a tolerance that you define for displacement to something that has forces in it, it will not really work. And it will be really hard to reach convergence because sometimes, most of the times, forces and displacement have different order of magnitude in terms of result. So this is another limitation of Lagrange multipliers. Wow, here is a wrong title. Sorry, guys. So with the transformation method instead, we have again a matrix condensation, exactly as before. So there's a reduction in the size of the matrix. But the point compared to the plain constraints is that the transformation method can be used also with non-homogeneous constraints. So also if you use prescribed displacements, for example. The only limitation is that in reference to the pairs and the nodes constrained in series, for example, if my node is constrained by a retained node, but it is also the retained node of another node. So this gets a bit complicated because the equation reference to that node gets erased, and then there's no reference for the next retained constraint pair to enforce, let's say, the constraint on the matrix. If the way the constraint is enforced is by erasing rows or equations, this means that you need to have all the rows available in the moment that they need to be erased. I'm sorry if I'm making a convoluted discussion on this. Please do stop me if something is not clear. I understand this is a very complex topic. This actually was really discussed by Massimo in another webinar that we have the link to it, of course. But it's important that we kind of spruce up all the contents before we go forward with our applications. Of course, here, given that we can use non-homogeneous constraints, the condensed DOFs can be different from 0. So there's less limitations than in the plain constraint handler. And then in the end, we have the penalty method. What happened in the penalty method? the matrix remains of the same exact size. It just gets kind of reordered. So, and the content gets a little bit changed. So what happens is that in order to enforce a constraint on a specific DOF, its values, it's increased by a large number in a way that it represents a very large stiffness. So let's say that this penalty method works numerically rather than physically, please do pass me the term, on the matrix. So this additional stiffness affects also the eigenvalues and the eigenvectors of the structure. So its value and its magnitude has to be really, really calibrated in order not to affect wrongly what happens in the transient analysis or in an eigenvalue analysis. So the choice of the penalty parameter is really important. But let's just remember that in comparison to the other handlers here, the matrix size remains the same, which is also, let's say, an improvement rather than increasing the matrix size and not having the possibility to store a very large model matrix. The limitation of the penalty method is that the only limitation, let's say, is that you cannot use the normal balance convergence test. This is because you're adding a very large value, let's say creating a lot of stiff springs in your model so that those constraints will behave as if they're infinitely rigid. Infinitely is not really possible, of course, numerically, but this will mean that in those constraint node, the forces will never go to zero. So it will be very difficult to pass a test that has a small tolerance in terms of forces. So do not try to run, this is the most common error on our forum, like you're trying to run a penalty handler with a normal balance test. This should never happen. And yes, there is another, this is not a limitation, to be honest, it's just an additional work that you have to do when you have to choose the penalty parameters. There is still not an automatic tool that does that for you, but we are planning on implementing it in STKO. What you have to do to define the penalty parameters, just let me maybe open STKO to show you. What you have to do to define the model parameters is identify which one is the highest stiffness in your model. So let's say in terms of your highest section and your higher stiffness parameter in your model, and then add the 8 number to it, which is not like a random number. It's actually the number of the significant values in a digital number. And these parameters should not be too high or too low, because they need to be large enough to be effective, like to be stiff enough so that they can constrain the nodes to each other, but not too large to cause numerical singularities in your model. Because if you have extremely, extremely high constraining forces, then it will be really hard to find convergence. I just wanted to show you here which are the penalty parameters. If you open an analysis command and pick the penalty method, you see you have alpha S and alpha M. These two parameters are normally chosen the same, and they need to be in the range of your highest stiffness of the model plus 8, a little less, a little low. And you can make some attempts at it. So you can see this is something that can be really done easily if you're running an eigenvalue analysis. You see what's the period of your structure, you see if it moves in a way that you kind of expect it to, if everything that you want it to be connected is connected. And like this, you can have, let's say, a comparison. So just to recap what we said about constraint handler, you can see here a bit of what are the differences, what does condensation, what does change the matrix size, what does adds a row, adds like, so increases the matrix size, what can and cannot be enforced with these kind of handlers, what you have to pay attention to and what you cannot use in terms of convergence tests. As you can see, the penalty method is the one that has the least limitations and is the one that we prefer to use, unless we do not have any multi-point constraints or any problems with retained constraint pairs, then we do use the transformation method. So let's say the first two are not for our everyday models. I see we have a question let me just check. One question: what type of problem is advised to use which each constraint handler? So as I said, it's not really reference to the type of structure. It's more reference to which kind of interactions are there. So which are the constraints that you are enforcing on it? You could have similar constraints in completely different structures. So it's not really about the type of model. It's more about if you have multiple constraints, if you need to enforce non-homogeneous constraints, if you have over constraints or nodes constrained in series, and if you want to use a specific conversion test or not. So this is the thing. And of course, if you have a very, very large model and you want to condensate your matrix, that's also another distinction. It does not really matter what's the type of model you're doing. Maybe we have another question? No, that's it. Okay, let's move forward. Oh, I did actually an explanatory slide. I forgot about it. So use the plane constraints only if you don't have multiplying constraints and prescribed displacement. Use the Lagrange multiply if you don't expect a very large matrix. Always use the transformation, in our opinion, if you don't have mixed pairs or constrained in series. And then always use the penalty method when you have multiplying constraints. But pay attention at penalty parameters. Of course, from the multiplying constraints I'm talking about, the equal DOF is excluded because that really does not represent this problem. I think we discussed this a lot. Let's go a bit further and see if we can at least talk about numbers before we take a little break. Just to add to this, what can happen if you choose it wrong? I already said, just already mentioned, but for example, this was a question on our forum. This is actually related to how an eigenvalue analysis is set up in the analysis steps. So it's not really related to the constraint handler itself, but depending on how you set up the eigenvalue analysis, you can actually use a constraint handler that is not the one that you picked by referring to the default one. And in this case, the wrong constraint handler actually determined the analysis to run and actually output results. But then when you went to see the results, they were not what you expected. So in this case, the multiple constraints of the rigid diaphragm was not enforced here because one of the handlers that cannot really support multiple constraints was used. Instead, here with the penalty method, we could reach actually a good result. So if you choose a wrong constraint handler, it does not mean that your analysis will not run. It just means that some of the constraints that you put may be skipped and you could get unexpected results. So it's really important to check. This is something I always say to people, like, and everybody says that if you learn numerical modeling, if you're doing a large model, even a very complex one, set everything to linear, run a simple gravity analysis and see that everything is connected and everything works as you expect it to, especially if you're trying to pick a right constraint handler. And another thing that can happen is that the matrix is singular and there is a warning for it. For example, when you use the plane constraint and you are actually producing a singular matrix because of the switch in the retained constraint nodes, then you will get a warning. But be careful because, for example, in the transformation method, in which you still have the same problem and you have to pay attention of the pair, then there's not a unique choice. And then there's not going to be a warning. There's going to be just a singularity, but you will not be able to tell why it is there. So if you're not really acquainted with OpenSees, you will not really know where does that come from. As I was saying, there's not a unique choice of handler. So there's not one handler that will work in any case. You will have to pick the one that you really need for each of your models. So going forward about numbers, this is really an easy concept. Let me check. Yeah, okay, we already answered this question. So what are numbers? A number is what determines how the DOFs are mapped in the global stiffness matrix. So how they are really like tagged. You can see in STKO when you turn on the tags that all the nodes are tagged according to an internal system that you don't really define when you draw. But if you're actually doing your own TICO scripts, those nodes are tagged by yourself. You are the one who assigns a node tag to your nodes. So what happens is that if you do it by hand, or if STKO does it anyway, it's really useful and convenient to have a system that renumbers all the DOFs in a way that can reorganize your matrix and obtain a sparse matrix. So a sparse matrix is a matrix that allocates only non-zero values in the machine memory of your computer, which reduces the computational cost of your analysis. So if you need to run a very large model, you really need your matrix to be a sparse one and to be renumbered in an optimized way. This is just an example of how big could be the space that you need to allocate a specific number of nodes. Each node has 6 DOFs. Of course, each of these is a number, so you actually need a lot of space for matrix transformation, factorization for the result. It's not just the matrix space, but it's actually a much larger space. So it can happen that if you are doing a too large model, you refine your mesh so much and you have so many elements that your computer will tell you, I have no more memory for this. And so using an appropriate number can help you a lot to reduce the size of your matrix. So there's 4 types of numbers. The one that we use the most is the reverse CuthillMckee. It optimizes the node numbering, also called RCM. It optimizes the node numbering and reduces the bandwidth using a numbering graph. And so if you have a large model, do use this one because you need to obtain a sparse matrix to cut on computational cost. What is also used is the parallel RCM, because if you need to run parallel analysis, you need a parallel number that will be able to actually renumber your nodes in a way that they can go on different processors. And then we have the plain number, which, let's say it's a bit arbitrary. It's based on the input file that you build. So in this case, it's based on the input file that STKO builds. And it's okay for small problems when you don't have a lot of DOFs. Or for some sparse solvers that do not have any internal DOFs numbering system. But if you wish to, for example, print a global matrix, this is the only way you can do it. So if you have a very small example, for example, a beam or a truss or a portal, and you want to build the matrix of your example, then you can use this plain number. It's the only one you can use to do this. Otherwise, your matrix will be renumbered and optimized, and you are not really going to see what's the global matrix of your structure. You're going to see the renumbered and compacted version of it. Let's take a little short pause. Let me check how many people are there. If there's someone that already has some questions, we can discuss something. I know it's kind of like very theoretical and abstract like this, but it's better to go through each of the steps at the beginning. Otherwise, you can find yourself like doing I don't know, a cyclic analysis or a transient analysis, and you don't know why you're using certain things instead of others. Maybe you're just copy pasting what's in an example that you find on our forum or on our website. I don't know if there's some newcomers, Naomi, Deepak, Jimmy. I don't know if you guys have something to ask. Okay, we're all good. Maybe we're gonna need less time this time. It means we can go to the beach afterwards. So, so going forward, let me drink a little water. So going forward, we have what are called system solvers. So they sound like a very complicated things, but they're not really. I mean, I cannot really explain them to you today in detail, but they're not really a complicated things. So what a system solver does is just find a way to solve the equations of our linear problem. of the linear system of equations that your FEM model is actually building, and then stores the solution somewhere, of course, in a matrix form. So it provides, let's say, a solution to the differential equation of your problem. The problem, so this matrix where this solution is stored, they have different characteristics. And so different solver can provide you with different types of matrices in which you can store your problem. If you have a specific type of matrix, your analysis can kind of change in terms of computational cost, in terms of how much time, the computational cost is the time, of course. Let's say computational cost both in terms of time and space, so time and memory on your computer. And also which kind of operations you can do on the matrix. So these are a few types of matrices that you can find in different solvers. And these are the types of solvers that we have in OpenSees. What we highlighted in blue is what we mostly use. So given that not everybody knows which kind of matrix your model will output, because it's really complicated, as we said before, to have I just found something in Italian here. Let's change it. Very fast. One partition, not in parallel. Sorry, guys. So what we mostly use are the SuperLU solver, the UMFPAC solver, which is the default one that you find in the analysis command, and the MUM solvers when we are running parallel analysis. The other solvers, they reference, for example, these three and this one, they reference specific type of matrices. So if your matrix is symmetric positive definite, is a band matrix, is a sparse symmetric matrix, or you're running unparalleled sparse symmetric positive definite matrix. So there's so many different types that reference a specific type of matrix that you want to enforce on your structure solution, and that if you're not really sure which is the matrix that you're looking for, these are the two solvers that we advise you to use, because they cover sparse asymmetrical matrices, which is often the case in complex research problems, for example, non-associated plasticity on the use of damage behavioral model for masonry, for example. So this one is a bit faster than the SuperLU, and of course you can use the MUMPS solver, which is the fastest solver that's available in OpenSees. And it's used for parallel computing, but if you create one single partition with our partition tool in STKO, you can still use the MUMPS. So your analysis will be run on one single processor, and you will be able to exploit the computational power of this solver. An extra thing to say about solvers, there is the full general option, which really you should never use if your model is large. And what I mean by large model, I mean like already 500 nodes is large. This means you cannot use this kind of solver because it requires a lot of memory, more than any other solvers put together. And so it will take a lot of time to actually run your analysis. But if you want to print the global matrix, if you watch Massimo's webinar, he really does an example on this, on how to print the stiffness matrix of a specific simple example, like a simple small model, and that can be really useful if you're learning. And so this is the only solver that will allow you to print the matrix. The other ones will not, because of course it will be full of zeros and compacted and very large. And that's not something you can actually see on the console of OpenSees. And it's not implemented inside that you are allowed to. So this one is the only solver that will actually help you do that. Then we are getting to what are solution algorithms. So once, let's say the solver provides the solution inside a specific solution algorithm framework. Because what the algorithm does is defining the sequence of steps that you need to solve the nonlinear equation system. So that you need to take to solve the nonlinear equation system. I don't know how many of you guys have experience with nonlinear analysis and nonlinear problems. There are many solution algorithms. These are not the one available in OpenSees are not even the only ones that are available in nonlinear finite element softwares. Let's say the most used one are the Newton algorithm and its modifications. And of course, if you have a linear problem, you can just directly use a linear algorithm because you will not really need to approximate the solution with any of these methods. So what happens is that all of these have different characteristics. They use a different kind of stiffness to approach the solution. So let's say if the stiffness updates at each step, if the stiffness remains the same at each step, like the initial one, or if the stiffness is found not with a tangent, but with a secant line in your curve. So there's actually many different distinctions on how this is done. And you can imagine, like intuitively, that if the stiffness has to be recalculated at each step, of course, the time of the computation will be higher, but the accuracy also will be higher. And instead, if you use the same stiffness for each step, that time will be lower. But of course, maybe you are not going to get specific point on the curves that you're trying to catch as your solution. What we use when we are having problems of convergence is the Cribler-Newton algorithm, because when we have softening behavior, it can be the best choice to approximate to reach the solution in a nonlinear problem. And of course, softening is a nonlinear problem. And you can have a faster analysis also because you can ask the algorithm not to update the matrix at each step, but you can ask to do that at a specific interval. So rather than, you can use the same stiffness for a certain portion of your analysis and then change it and change it and change it in a range, rather than doing it at each step, avoiding some instability problems. So what we can tell you about the types and the definition is that this is something we use when you have complex problems. This is what you use when you have only linear problems. And these are algorithms you can attempt to use to see what is it that reaches better convergence in your model. There's a lot of literature on this. A lot of people studied this topic, so it's not really our job to teach how each of these algorithms works. Just so you know, in OpenSees, there's not like an incompatibility between the setup of an algorithm and the rest of your model. Of course, if you've input linearities in terms of material or in terms of geometry, you cannot use a linear solution algorithm. This is, I think, basic concept. And finally, we can discuss.
Can I ask you a question?
Of course.
Before we move on. Regarding this solutions algorithm, could be a problem like in the results I get with the stiffness of the curve I get if I choose wrongly this type of solution? Could have an impact?
So it's not about the wrong or the right. So you know that the solution, the numerical solution is always an approximated solution. So what I can say from my experience is that sometimes you can reach higher values of a pushover curve if you change a solution algorithm. And that just means that your solution is, of course, sensitive to the choice of algorithm that you're using. That does not mean that the result is not correct or wrong. And there's actually, there's some literature on comparisons on, I don't know, if I use quasi-secant Newton, I can reach solution faster, but I don't go as far. And for example, opposite, if I use a Newton-Raphson algorithm, I'm going to reach the further displacement of my curve, but the analysis will take ages. So it's a bit of a trade-off between accuracy of the result and computational cost. And this is true for any numerical analysis. It's not just for OpenSees, at least to my knowledge.
Okay, so the thing is, even if normally, well, now I'm always using the Cribler-Newton, but for example, with Diana, I'm using the quasi-tangent one. So I was thinking that maybe if I change, like I'm using this one because in all the examples we are always using this one because of the nonlinearity thing. But may I like the thing is, should I change this solution to see if I get something different? And
I mean, if you want to compare your results in Diana with your results in OpenSees, of course, it would be best if you use the same algorithm, because like they are, I guess, I don't know how they are enforcing Diana, because they have a lot of documentation though on how they are actually implemented inside of the software. You can make a comparison between how the command is built in OpenSees. If you go and look in the OpenSees source code and try to read a bit, the C++ is a bit complicated, but you can try. And I would say, yeah, if you have to make a comparison between two models, it's better if you use the same algorithms, especially if in Diana you are don't have the one that you're using available in OpenSees. So
okay. No, because I thought that maybe I had some weird solutions regarding a pushover curve, and I'm always using this one. And now that you said this, I thought like, okay, maybe I'm using the wrong solution algorithm.
Not be comparable or similar to the one that you find with the other algorithm. So at least to my knowledge, it's not like it changes so much that you need to actually be careful on which one you use.
Okay.
As for the question of Hernan, how to obtain the stiffness and mass matrix from a model in OpenSees. So what I can suggest you to do for this question is to go on Professor Scott Portswood Digital. This is Professor Scott's blog. I think it's called let me check if I find, well, let me check in the search if there's a search here. Give me all your damping and your mass and stiffness too. Its titles are really, really nice all the time. So here you can find an explanation of the printA function, which is a function that you can use, added a few years ago, as it says here, to actually output the matrix of your structure. It's not really easy, like it's not really like straightforward, but the article is not so long, so you can try and read it and apply the code if you're using OpenSees Spy. Or there's also another thing I can point you to, learning as there. Like here in this webinar from Dr. Petracca, it's called number 13, Common Errors and Convergence Issue in OpenSees and STKO. If you go here, actually, I have this file in my computer. Let me show you very quickly. Desktop. So here, this was an easy custom command that you can add in STKO, like we discussed last week. You add custom commands. And this one, we use the function printA to print on a file and also in the console the matrix of your structure. So you will be able to see it. But as I said in my presentation here, this works only if you're using this kind of solver, and it works only if your model is quite small, because if your model is very big, you will not be able to allocate enough space to print the matrix. Not just to print the matrix, but to run the analysis and build the matrix. Because if the matrix is so large and it gets built like in its full shape without being optimized in any way, it has a sparse matrix, that's actually becomes very complicated to handle on a normal computer. So I hope this answers your question. I don't remember who was asking.
Thank you very much. Yeah, it was Hernan. Thank you very much.
Fine. Why do you want to print your matrix?
It's to compare with the other model. Sometimes I use the matrix and I want to use it using in another software. So
Like
and also
running some code on
for
MATLAB?
teaching. Yeah, exactly. And also for teaching, I teach and then for small models, it's useful to define or to show the stiffness in mass matrices.
Like if you go in this webinar, I'm just gonna point you in the right place because this one does not have timestamps, so it will be fast difficult for you to find the point. I remember that, yeah, at some point here, yeah, he was starting to print the matrix using different handlers. So if you see, for example, here, he has a single truss model and he's printing the matrix here. So yeah, you can actually watch this around minute 50 and it will make an explanation of the use of this. The point of this model was actually to make a comparison in between the different handlers and see how they change the matrix. So you can see it decreasing and increasing, etc. But that's also going to be useful to actually understand how to use it. But remember that it has to be a matrix that has, I don't know, a size that's like humanly understandable.
Yes, yes, thank you.
Okay, we can go forward with our last topic of today, which is convergence test. So what does a convergence test do? It actually is the let's say, it's the thing that allows you to move from one step to the next in your analysis, and it determines if the convergence is actually being achieved or not against a specific tolerance that you pick. So it's not something that is done automatically by the software. It's always a user choice. There are, let's say, three main type of convergence tests. This is something that is in any nonlinear finite element software. You can test the imbalance, so the forces. You can test the displacement, so the displacement, or you can test the energy, which comes down actually to a product of forces and displacement. So you're kind of testing three different quantities at each step of your analysis. So what the test does is like inspecting all the results and checking if the norm in between one step and the other has an error that's comparable to your tolerance and lower than it. There's some limitations. We already talked about how the handler cannot be used with some specific handler cannot be used with some specific convergence test. So if you are using the penalty, so adding large stiffness in your matrices, you cannot really test on the forces because you're gonna have super high forces and they're never gonna test convergent to it. And if you're using the Lagrange multiplier, you cannot really use the displacement increment test. There's also another type of test, which are the relative norms. Those tests actually test the ratio of the error at the time step against the initial error. So because you assume that at the first step of your analysis, you have a very small error because you're just starting. And then you kind of check each step against that initial error, but you need to be careful about what was the, let's say, the order of magnitude of the initial error that you want to have. Also, always referencing to the forces, displacement, or energy. There's the total relative, which we don't really use so much. And then there's the fixed number of iteration, which I actually put a funny icon here because it's a bit of a gamble. So you're actually just saying, I want my analysis to be stopped after 100 iterations, whatever is the result that I'm getting. And I don't know, that's not really something that we suggest you to use. You have to be careful with the units of the tolerance that you impose, because if you're running a model in millimeters and you're imposing a tolerance of the 10 to the power of 9, then that's really a small number for a millimeter, and that's never going to converge. So the tolerance is applied to the results, and the results are in the units that you defined at the beginning. Then, of course, if you're using energy tests, you also have to be careful with the order of magnitude of your tolerance.
Francesca,
Yeah.
Can you explain that again about the tolerance and the units?
So let's say the convergence test, it's actually telling you what kind of error can you accept in your numerical analysis. So we all know that numerical analysis are always have some kind of error for them, because of course the numbers that a computer can handle have a finite dimension. So you cannot really go to the infinite after the comma decimal. And so, and not only for that, but also because numerically it's an approximation of something that you don't know, and you're actually linearizing something that's not linear. So what you do is you say, after each step, I want my error to be less than this. And if you are doing a model that it's in meter and you say, I want my error on the displacement results. So let's say, how can I explain you better? I want.
I tell you why I'm asking.
Yeah.
Because maybe it's easier for you to explain me.
Yeah.
Because I think I had an error related with this, and my model was in meters, but the displacement I was imposing, so if they were in millimeters, so I turned it into meters to impose it because my model was in meters. But then I had an error related to this, like it was not able to converge because I think this was really small. So the thing is, which is the my number there has to be related with the fact that I'm working in meters, but the displacement I'm looking for is in millimeters.
No. So what the result you get is in the units that you set up your model in. So if you modeled in meters, the result in terms of displacement will be in meters. And everything you had applied that has a length has to be in meters. Okay, so this means that when you are testing on the displacement error, so you want that error to be small, like in I don't know, as with common sense, you say, okay, maybe 0.003 millimeter is an okay error for my structure. And so you test for 10 to the -6 because you're in meters. So you have to go down 3 order of magnitude from millimeters, let's say. But if you're in millimeters and you keep that 10 to the power -6, then you're trying to test at 0.000001 millimeter. And that's really small, and that's really ambitious to ask a numerical model to actually provide you such a precise solution.
I understood. No. Okay. Yeah.
So there's only
I know
to those two things.
Okay. So I know what I have to think about independent, because I did everything in meters, but then I was imposing something in meters, and then I realized I should impose millimeters, so I changed that. But I never. Yeah. This is the thing. I was imposing 10 millimeters, but I was imposing 10 meters, so it was crazy. And so then I have to adjust this tolerance to what I'm expecting. Okay.
Of course.
Thank you.
But then all in the same unit of what you set up for your model. And this same goes for the energy. So if you have forces in one unit and your displacement in another unit, you know that the energy is a product of these two. And the energy test is, let's say, a bit less restrictive in the sense that you can achieve better convergence because you have lower errors in terms of energy. But you have to be careful, because if the order of magnitudes of your forces and displacement are different, I don't know, for some reason you're using kilonewtons and millimeters, then you have, I mean, I don't know who would do that, but it can happen. So then when you test on energy, you have to actually think about, okay, if I want an error of 0.001 Newton, but I'm kilonewton, so I have to put that really low, and then I have to product that for my error in millimeters, and I'll get a specific number. So most probably when you test on energy, you will have a larger tolerance number than when you test on displacement and forces. And of course, once again, as we said before, you have to check on the combination between your constraint handler and your convergence test. So I'm actually done with my presentation. It took less time than I expected because I don't know, I was afraid that explaining these topics would actually require one entire hour, which it actually did, but we already had some discussion. I don't know if there's some people that just came in, David and Mariana. If you guys have want a little recap, or if you already have questions on this topic, I can show you let's say this was the content of our presentation today. We didn't have any practical examples, but if you already have some interesting questions, some other, because you all guys already did some. We're just gonna wait a little minute. I'm sorry if someone thought it was at 6 and maybe got a little late from 6. The change in time was to allow more space for discussion. Okay, so do you guys have any other not topic related questions or any feedback you want to give? Or
Integrators, we're going to discuss it next week.
yes,
Okay.
because integrators do differ if you're doing static or transient. Instead, all of this setup you can either use for static or for transient. They do not differ if you're doing a static or dynamic analysis. Well, I mean, there's a little concept that that to take conscious of about the penalty method, because how it enforces the constraint is by inserting very, very large and stiff numbers in the matrix. So this means that if that number of large stiffness is not calibrated properly, this can lead to an impact on the eigenvalue of the structure. So if you're doing a transient analysis, then your inertial forces will kind of be messed up if you're not taking care of defining the number correctly. So it's actually useful if you have, for example, a model with multiple constraints, and then you have and you want to do a dynamic analysis on it. What can be useful is to do an analysis with the transformation method without the multiple constraints, just to see the order of magnitude of your results, and then actually apply your interaction. Of course, sometimes it's not possible, like you cannot really make a comparison with and without the interaction, but if you can, you can try, maybe, I don't know, instead of using rigid diaphragm, you can try to use shell and see if the order of magnitude of your result is comparable. Then it means that the penalty parameters that you're using are well calibrated. I'm sorry for the people who arrived just right now, because we're almost done. I don't know if you want me to make a quick recap if you're interested, otherwise the video will be up tomorrow on YouTube. We have a question: does all those tolerance values for test command on STKO default value for meters and kilonewtons? Absolutely no. So let's check in the presentation. I already have the default. Yeah, the default is 10 to the power of -3, but that's just because I don't know, we assume people model in neuron and millimeters. So 10 to the -3, it's good, has a tolerance that you want 0.003 millimeter error. So actually the default are for millimeters and newtons, not meter and kilonewtons. I don't know about actually the other ones, because that was the default for the normal balance. I guess the default is the same for all. And it's okay if you are actually doing a model. Actually, this is a very good question, because I said that if you open the analysis command, you can run any static gravity analysis as it is. No, if you're modeling in, I don't know, micrometers, that would not be good because you're trying to reach a very small value of convergence. But yeah, so just never trust the default values.
I have one question.
Okay.
Thank you first for the presentation. It was very useful for all of us, I think. If I want to use, like in OpenSees, you have, for example, I have a specific problem related with the Drucker-Prager model. And this Drucker-Prager model has some constants that need to be filled. I don't know if STKO presents a little bit more information about these constants in order to fill them, because I tried to look for these characteristics, especially for the softening behavior of the Drucker-Prager model, but there is not too much literature explaining how to fit these constants. So maybe you can help me with this.
Well, I mean, me right now, I don't know if I can really help you with the answer of how to do the constants, but to calibrate them and define their values. But of course, if you posted the question on our forum, we can find some literature for you and maybe some examples. I don't have experience with that model too. I haven't actually applied it, so I have never had to set the constant value myself. So we can help you. Just post a question on our forum and we can do some research for you and see what's there in the OpenSees world.
Thank you very much.
You're welcome.
I have another question, if possible.
You have time.
Because I'm thinking of the models I have to run to see if the errors I have is because of I'm not matching correctly the handlers and the solvers. So every time I have a prescribed displacement in my model, I cannot use, I should use penalty because the others have problems with
with this prescribed displacement, the only one that has really problems is the plane constraints.
The planes, well, yes, but if I have the prescribed displacement and multiple constraints,
yeah,
I should use penalty.
Yeah, unless your multiple constraints is an equal DOF.
Ah, okay, yes. And in the case I'm using the penalty, my conversion test should be displacement or energy, not unbalanced like forces.
Yes, this is because in the matrix that you are building, the forces on the constraint node will never really go to zero because you have an infinite stiffness. So you cannot use that kind of test because you will never reach the conversions, and that's not because you model it wrong or it's failing, but because it doesn't really work numerically.
Okay, and if I do that, should I have, because what I'm thinking is if I want to prescribe if I have a multiple points constraint and I want to impose a displacement, but I also want to see the run an eigenvalue analysis, I cannot use the same.
Yeah, you can use the penalty for the eigenvalue, just
even if it affects the eigen, because I wrote it affects the eigenvalue analysis. So
it does affect. Think about it. You're actually saying my model is super stiff here. What is that an eigenvalue result is in terms of the stiffness of your structures? Like it's telling you how dynamic intrinsic characteristics are depending on stiffness of the structure. So if you want to know the eigenvalues of your structure and you're inserting a super high stiffness inside of it, that's of course be affected. But if you put them in the right order of magnitude, it's not that the result is wrong. It's actually going to be correct. It's just that if you apply too lower stiffness, then your structure will yield a result that's not really realistic, because it's like you're saying, I want this node to be fixed to this other node, and they have to move exactly the same. but the stiffness I put in between is not strong enough in compared to the size of my model in terms of stiffness to actually be comparable and be like if you want to have a fix, think about it numerically. If the stiffness of your structure is to the power of 6 and you want to fix something in that order of numbers, you need something much higher than that, but not infinite. Otherwise, the handler will not work. So that's the only point. Like they affect the eigenvalue, but if you actually are in the right order of magnitude, the result is okay.
So it should be convenient for me first to run an eigenvalue analysis, see which are the results with the corresponding solver and handler, and then change to the other one to have everything and check that they match.
Run analysis with different penalty parameters and see how the norm changes. For example, if you're doing a linear analysis, you know that your error has to be small because it's moving very like linearly. There's no really much problem. So the norm in this case, in terms of displacement, will be small, like to the power of -12 or -15. So if you have the wrong penalty parameters and you're running with the displacement norm, but your model is linear, so you don't expect your norm to be big like to the -5 or -4, then what happens is that if you have the wrong penalty, you will see that norm being small because it's having a problem enforcing that stiffness that you applied to it. So just check that the result that you get is consistent with the setup that you are giving. So if your model is linear, the norm is super small. And so that means also that the penalty parameter is correct. And if you change it like about one number or two, like -14, -15, -16, and compare the results, then you can kind of have an idea of first how the analysis is running, and second, if the order of magnitude of the result is comparable, because you will see your result changing if you like go much farther from that optimum medium value.
Okay, thank you.
It's a lot of runs, but it's quite fast. So, I mean, depends on the model.
Well, it's a simple one. So I've done one, and I'm comparing it with Diana, and so I want to see that I'm not like by choosing a wrong handler, I'm not making a mistake. That is not the model, but myself that is the one that's choosing the wrong handler and solver. So I need to check all of these things so I can be sure that the values I'm getting are the right ones. So this is why I was asking.
I mean, if you look in the OpenSees manual, it does says we do not advise to use the penalty method for transient analysis. So this is an issue. But I think if you calibrate it well, then it's actually acceptable as a result. Is anybody else curious about something? Do you want a short recap? If you arrived late. So the video will be uploaded just tomorrow, just the time to save the recording, edit it, and put timestamps and put it online. So no problem. No problem, Mariana. You will be able to see it tomorrow. If you do have questions, you can comment under the YouTube video too, and we will get to it, like not maybe on the same day, but we can answer to those.
One more question. Where do I find the forum where I can make my...
Yes, of course. So if you go on our website, as there, you click on train support. You can click on STKO forum here, and we have actually our own, let's say, section of the forum. It's not being much used, to be honest, but anyway, the other ones are, so you can see there's so many posts. If you have questions about something, that's also very useful to go and read what is it that people have asked before and what are the answers that we gave to them, because it can be, maybe you already find your problem. This is another model in which there was the same problem of wrong handler impose. You see all of these braces were not attached to the structure. Instead, when changing the handler, this did not happen anymore. And so you can find a lot of examples actually from models built by other people and corrected by us. So it's a big container of information. Do you just have to register? And if you have problems because of, I don't know, sometimes with people with the VPN or stuff like that, they have problems, you can just email us and we can help you with to solve your issue. Yeah, and Anna also just posted the forum link in the chat. So do click
Thank
there.
you very much. Thank you.
Okay, guys, I think we are done for today. We can discuss next week the rest of the analysis command. Then the week after we discuss results, and then we go on holidays. And when we're back, we can actually do something, like something practical. Thank you for participating and have a good rest of the week.
Thank you very much.
Ciao.
Ciao.